Welcome back to optimization for deep learning. So in this lecture, we're going to talk a little bit about some optimization basics that we need in this course. Okay. So the first concept that I want to talk about is the concept of stationary points. So let's consider an optimization problem where I want to minimize a loss function. So here, where my decision variable is w, and we assume that there is no constraints, meaning that w is just a vector in Rd. So the size of w is d, okay? And we want to solve this problem. So what does that mean to solve it, right? So essentially, we want to find an optimal solution that achieves the lowest function value, okay? In many cases, this could be a very, very ambitious goal, certainly in problems in deep learning and machine learning, because of how complex our function is. So therefore, it is useful to first define a more broad definition that potentially is easier to achieve. And that's the concept of a stationary solution, okay? So we say W star is a stationary point, or more accurately, a first order stationary point, if the gradient of the function, or essentially derivative if you're more comfortable with, at W star is 0. So that means that this condition must be satisfied. The gradient of f at W star has to be 0, okay? Then we call W star a first order stationary point. We call it first order because we are talking about the condition that has to be satisfied for the gradient, right? So, and gradient is essentially a first order information, something about the first order derivative of a function. Okay. Now you can talk about solutions that are a higher quality or lower quality, because the stationary point doesn't provide any information about this solution is a good solution or a bad solution, if it's optimal or not, okay? For instance, let me draw a function here, very simple function, okay? Here, you should think of gradient being 0 as a tangent line to the function with the slope 0, okay? So all of these points are essentially stationary solutions, okay? So let's call them W1, W2, W3, W4. All of these solutions satisfy our first order stationarity, okay? But they're not all the same. Intuitively, some are better than the others. In particular, if I want to minimize a function, W1 and W3 are not good solutions because locally they are actually maximizing the function, okay? On the other hand, W4 and W2 are better in the sense that at least locally they are minimizing the function. And between W2 and W4, obviously, as we can see here, W2 is a better solution because it achieves a lower function value, right? So therefore, stationarity is a condition that is a necessary condition for optimality, but it is not going to be sufficient in general. Therefore, we may need other conditions to be satisfied if you're looking for higher quality solutions. And in a lot of cases, we need more information, right? So because we are pursuing a more ambitious goal. One piece of information that is useful for us to determine at least whether locally a solution is a good solution or not is second order information, the information provided by the second order derivative or the Hessian of a function, okay? In particular, if I'm able to calculate the Hessian of the function at W star, if the Hessian is positive definite, then W star is a local minimum. On the other hand, if the Hessian is negative definite, W star is a local maximum. So for this example that I drew here, you can imagine that the Hessian at W1, and so let me write it here, the Hessian at W1 is less than 0, and I have a local maximum. On the other hand, the Hessian at W2 is positive definite. So the curvature is upward here, versus the curvature here is downward. So therefore, W2 is a local minimum. So that's why W2 is a better solution than W1. Okay. Now, this condition sometimes could be referred to as a second-order stationarity, meaning that you have a solution that is a first-order stationary point, meaning that the gradient is 0. Also, it is at that solution, the Hessian is positive definite, meaning that the curvature is sort of curving upward. Okay, and this is something we're going to talk a little bit more deeply as we progress in the course. But for the first few lectures, I would say this is not of essential importance for us. All right, and this is a point that I mentioned that is important to note, that the stationary point, even a local minimum, is not necessarily an optimal solution. And we illustrated this, this fact in this simple function. For instance, W4 is a stationary point. The gradient is 0. It's also a local minimum. The Hessian is positive. But it's not a global solution. In fact, W2 is a global solution. Okay. Now, sometimes we have functions that are very complicated like this. So therefore, in the worst case, we may not be able to even characterize very efficiently whether a solution is a global minimum or not. But in other cases, we have functions that actually are very easy to tell whether a specific point is their global solution or not. Okay? And these are convex functions that I'm going to talk a little bit about them here. And the main reason is that I want to distinguish these type of functions with the from the functions that we typically deal with in deep learning, which are non-convex. Okay? And that's why to understand deep learning, we actually have to develop an understanding of non-convex or model optimization theory, as opposed to traditional approaches and theorems that are mostly concerned with understanding convex loss functions. Okay, so let's talk about first the convexity of sets, and then we're going to talk about the convexity of functions. Okay, so what are convex sets? Let's consider a set X, and we call that convex if for all points xi that belong to X, the convex combination of the points also belong to X. Okay, so what is convex combination? It means that I defined a set of weights, Wi's, that are non-negative, and they sum to 1. Then the convex combination of xi's is essentially this weighted combination that I have here. So this is the convex combination. So a set is convex if and only if the convex combination, arbitrary convex combination of the points that belong to the set also belongs to that set. Let me try to illustrate this with simple examples. For instance, let's consider a set like this. Okay, so any 2 points that you give me, okay, x1, x2, for instance, the midpoint or the line segment between the 2 points always resides inside the set. So therefore, this is an example of a convex set. And sometimes I write CVX as a shorthand notation for convexity. So let's compare it with compare this set with this example. Okay. Here, if you consider these 2 points, the line segment again belongs to the set. But that's not the whole story. If I consider these 2 points, part of the line segments resides outside of the set. Therefore, this is an example of a non-convex set. Okay. All right. Now let's talk about convex functions. Okay. And I will say that again, my definitions here are not very sometimes very precise. I'll just try to convey the main concepts that we need in this course. Okay. But let's talk about convex functions. So a function is convex, and for the timing, please ignore what I've written here in orange, and I'm going to discuss it in a minute. So a function is convex if for all xi's, the f of convex combination is less than or equal to the convex combination of the function values. Okay. So the way to illustrate this is as follows. Again, so imagine that I have a function like this. So this is f. So this says that if I consider any 2 points, let's call them x1 and x2, the value of the function at the midpoint, so let's say this is the midpoint, and this is the value of the function at the midpoint. Okay, and so these are the value of the function at x1 and x2. So the value of the function at the midpoint is lower than the average of the function values. Okay, so here the average function value is essentially something like this. So here is f of x1 plus f of x2 divided by 2. So that's what it says, that there is always this gap or some gap between the value of the function at the midpoint and the average of the function values. Okay, so these equations are essentially a way to generalize this idea to more than 2 points. Okay. Now we can have functions that are even nicer. So we haven't talked about why convex functions are nice, right? So but we're going to talk about that. But we can have functions that are even more convex, if you will, than this, right? And then we call them a strongly convex function, which requires us to alter this definition by replacing this inequality with a strict inequality. So this essentially says that if I consider 2 points, f of x1 plus x2 divided by 2 is strictly less than the average of function values. Okay, and in fact, the example that I'm showing here is an example of a strongly convex function, where there is always this non-zero gap between these two values. All right. So convex functions can be characterized using multiple equivalent definitions, and sometimes one definition is more useful in terms of, let's say, the, theoretical analysis of optimization algorithms, in terms of assessing the quality of the solution, etc. So therefore, let's also talk about those two other equivalent definitions of strong convex functions and also convex functions. Okay. Now, the second equivalent definition says that a function is convex if the function value at y is larger than or equal to this linear function. Okay. Now let's try to illustrate what this means. Again, let's consider our function f, and let's consider a point x. So this is point x. What this is saying is that if I consider a tangent line at this point, and this tangent line is essentially nothing but fx plus the inner product between the gradient of x, f at x, and y minus x. So this is basically the formula for this tangent line at x as a function of y. So this definition says that a function is convex such if the function always lies above the tangent line. Okay? And the function is strongly convex where there is a non-negligible gap or non-zero gap between the tangent line and the function value. Okay? And the gap can be mathematically described by adding this term to the definition of a convex function, where mu is called the strong convexity parameter, and essentially mu determines the extent of the function being strongly convex. Okay, so intuitively we want mu to be as large as possible because that would mean that the function is nicer in some sense. Okay, there is a larger gap between the function and its tangent. Okay. Now, one thing I want to mention here is that this definition is typically easier to work with than the first one we saw in the previous slide. But this also requires that your function is differentiable, okay? Whereas the previous one didn't. It only involved function values. And for this reason, the first definition is sometimes referred to as a zero-order definition of convex function. This is called the first-order definition of a convex function because the first one only has requirement on the function values. This has requirements involving the gradient as well. Now, in a similar vein, then we can talk about second-order definitions of a convex function. So, in particular, if I have a function which is twice differentiable, it is convex if for all. Sorry, this has to be if for all x, the Hessian is positive semi-definite. Okay. Let's try to illustrate what this means. So this means that basically the function is curving upward. Okay. So this is an example of a convex function. Okay. Whereas if I had a function that was, let's say, concave, so this is concave. As we can see, the curvature is curving downwards. Okay. So positive definition of the Hessian is essentially saying something about the curvature of the function. And similar to the previous definitions, a strongly convex function is one where the Hessian is not only positive semi-definite, but it's actually positive definite. So in some sense, we are replacing this inequality with a strict inequality as well. All right. So we spent a little bit talking about convex functions. And the reason for that is that convex functions are very, very nice in some sense. That is to say that if I have some local information about the quality of the solution, that local information provides certain global information. more specifically, if we have a stationary point, W star, which again can be identified locally if you just know the gradient of the function at that point. Then, if the function is additionally convex, this solution is going to be a global minimum, a condition that requires global information about the function, okay? And the proof is actually very, very simple to see. For instance, let's consider the first order definition of a convex function, okay? Now, this applies for any y and W star. I assume that W star is a solution which is a first order solution, meaning that the gradient is 0. So if we replace the gradient to be 0, what we're going to get is that f of y is less than or equal to f of W star for all y. So for any other solution y, the value that I get is going to be larger than the value that I get from this stationary point, okay? So that's why convex functions are very, very nice, that from local information, essentially information about whether a solution is stationary point or not, we can provide a global assessment about the quality of the solution. We can say with certainty that the solution is actually a global solution. In other words, for convex function, first order stationarity is not only a necessary condition, but it's actually also a sufficient condition for optimality. Now, strongly convex functions are actually even nicer in the sense that they're going to have a unique minimizer. Whereas for convex function, the solutions may actually be infinite. The solution set could be infinite. Let me try to illustrate this, right? So an example of a strongly convex function is a quadratic function. Let's call it f of x is equal to x squared. Now, this is my unique global solution. Whereas I can give you a function which is convex, something like this. Oops, sorry. Something like this, where all of these points are actually global solutions. So we have not only one, but an infinite number of solutions, despite the function being convex. So therefore, strongly convex functions are actually also nicer than convex functions. Not only we can guarantee optimality of a solution by just looking at this local information, the gradient value, but we can also say with certainty that solution is the unique minimizer. All right, but unfortunately, convexity is not something that we typically see when we talk about optimization problems when training deep learning models, okay? And the reason I talk about convexity is, again, to distinguish it from the loss functions that we typically deal with when analyzing deep learning training problems. Therefore, there is a need to go beyond the typical study of convex functions and the performance of algorithms for convex problems in order to understand why the training algorithms that we have work well on optimizing deep learning models. Okay. The next thing I want to talk about is notions of convergence, right? So when I say an algorithm is good, what does that mean? Okay. So in many cases in this course, we are interested in establishing the following, that certain error function or a convergence criterion is less than epsilon. So you have a target accuracy epsilon in mind, and you want to say that I want to find a solution W tilde such that according to a specific convergence notion error, the solution is an epsilon approximate solution, okay? Meaning that this criterion is very, very small. Okay? Now, the methods achieving these goals are typically iterative. So what does that mean? It means that they're going to make progress, gradual progress, to finding this W tilde. So, for instance, one of their parameters is the total number of iterations that you have to run an algorithm, right? So you start somewhere, you run the algorithm once, find hopefully a better solution. You run the algorithm for another iteration. Hopefully you keep improving upon the quality of this solution, and so on and so forth. And you repeat your process for, let's say, T iterations. And then at the end, you're going to output W tilde to be your approximate solution. Okay? And we're going to see numerous examples of these iterative methods in this course. Okay? Now, typically, better accuracy, meaning lower epsilon, requires you to run your algorithm for longer, for more iterations. Okay. Now, one of the goals in optimization, and also in optimization for deep learning, is to establish convergence rates, meaning provide a relation between T and epsilon according to different convergence criteria. Okay. Now, there is a terminology here when talking about convergence rates. So you can have sublinear rates and, let's say, linear rates. So these two are of more importance to us in this course. So sublinear rates means that the relation between T and epsilon is as follows, right? So T, the number of iterations that you have to run your algorithm, is at most epsilon to some power minus A. For some A, for some strictly positive A. For instance, you can say that T is sort of proportional to 1 over epsilon, okay? Or you can say T is proportional to 1 over epsilon square. These are all examples of sublinear rates, okay? On the other hand, you can have linear rates where you have a much better dependence on epsilon, okay? So why is it a much better dependence? For instance, imagine that epsilon is, or your target accuracy is 1 over 100, okay? Then this guy, or this rate, implies that you have to run your algorithm for T equal to 100 iterations. Whereas the linear rate says that you have to run your algorithm for something like log of 100, okay? Which is significantly smaller, okay? So therefore, we desire algorithms that have linear, or we prefer algorithms that enjoy linear rates compared to sublinear rates. Unfortunately, that's not typically the case when it comes to optimization problems that we deal with when training deep learning models. All right, so this is an example of linear versus sublinear rates. Let's also talk a little bit about some examples of these convergence criteria, or the error functions that we deal with in this course. The first example is essentially has something to do with approximate first order. So all I care about is to find a solution W tilde where the gradient norm is at most epsilon, okay? And again, this just says that your solution is going to be approximately first order solution. Could be local minimum, could be global minimum, could be even local maximum. But hopefully our algorithms are such that we can avoid bad solutions such as local maximum if we are minimizing a function, okay? And this criterion, I would say, is of utility when you are talking about general functions that are not necessarily convex, okay? So therefore, the most you can say about the performance of a specific algorithm is whether they can find a first order solution or not. Another criterion is when you require a low suboptimality gap, meaning that you want to find solution W tilde such that the value of the function at that point minus the optimal value is at most epsilon. Okay, and typically this f star, the optimal value, is equal to 0 in learning problems that we deal with in machine learning and deep learning, right? So essentially, the best that could happen is that you can fit the training data perfectly. So the loss value is, in the base case, equal to 0. And this, I would say, is pertinent when your function is convex or it is non-convex but has certain structures, such that you can leverage those structures to establish this more ambitious convergence property. And finally, you can talk about pointwise error, where you want to say that let's consider an optimal solution W star. I want to see how close my solution W tilde is to this specific solution W star. Now, in general, the number of global solutions is not one, so we may have an infinite number of them. So I would say, therefore, this condition is more pertinent when you are talking about strongly convex functions, where it is guaranteed that you have a unique minimizer, or you are focusing on a specific regions in the loss landscape, such that you can assume there is only a single solution, and you want to see how your the solution written by your algorithm, or how far the solution written by your algorithm is to that specific solution. So we're going to deal with some of these notions in this course, but I would say for the most part, because we are talking about non-convex functions, this is the convergence criteria that we're going to pay a lot more attention to. All right. Now let's talk about optimization as fixed point problems that you may have seen in your previous studies. Okay. And the reason I'm talking about is that this is a nice way to talk about one basic algorithm that underlines almost all of the training algorithms that we use and leverage when training deep learning models, and that's gradient descent. So let's consider our optimization problem again. So we are minimizing some loss function f for a decision variable which is d-dimensional, and there is no other constraints. Now, as we talked about, a necessary condition for optimality is first order heterogeneity, meaning that if W star is an optimal solution, it must be the case that the gradient of the function at W star is 0. Now, you can do something strange here. Let's say that I multiply this by some constant eta, where eta is, let's say, strictly positive. And then I subtract, let's say, W star from both sides. It is easy to see that these two conditions are equivalent, right? Now, one good thing about equation 12 compared to equation 11 is that now we can think of the task of finding a stationary point as the task of finding the fixed points of another function g, which takes this form, right? So essentially, the goal is find W star such that W star is equal to f of W star. And this is called the fixed point calculation problem. The simplest method for this is called fixed point iteration, where you iteratively apply your function to find the fixed point. You start at some W1, you feed it to the function g, and then that gives you W2, the next solution. And you keep doing this process over and over again until hopefully you converge to a solution. Now, for this specific function that we defined here, this fixed point iteration method leads to this update. WT plus 1 is, or the next solution, is the solution that you currently have minus eta. So this is the constant we use here, times the gradient of the function. And this method is called gradient descent with a step size or learning rate eta. Okay, and as I mentioned, this serves as a foundation of almost all of the deep learning training methods, some of which we're going to talk about and study in this course. So in the next lectures, we're going to talk about some basics of machine learning, and then we're going to talk about gradient descent a little bit more deeply. Thank you.